Good morning. Welcome back. Last time we had gone through the first parts of chapter 20. We'd gone through heat engines, looked at entropy and what that told us. And now, today what we want to do is finish up chapter 20. And we're going to be looking at refrigerators. Now, the first statement, we looked at a little bit of this last time. Just want to pick up and review a bit. Refrigerators can be analyzed as if they're heat engines operating in reverse, whatever that means. And what that does mean is we're transferring heat from an already cold environment, a region that's already at a lower temperature. It doesn't have to be cold, but at a lower temperature, we're transferring heat out and moving it into a higher temperature environment. So it's kind of backwards. You'd think, well, wait, isn't that backwards compared with how things are supposed to work? And we do that by plugging in the refrigerator. Now, as long as we've got refrigerators listed here, air conditioners work the same way, as do heat pumps. Now, heat pumps are really interesting devices. We'll have some more things to say about those. So last time we went through this too, but it's such a useful piece of technology. I think it's worth repeating. Here's a refrigerator. I'm going to plug it in. What the refrigerator does when I plug it in is it begins to operate a compressor. There is a vapor or a liquid coolant inside this tubing, and what the compressor does is it pumps on this coolant, and it pushes and creates a region of coolant at high pressure and high temperature. So by doing a lot of work, right, we're compressing this material, and when you compress it, temperature takes off. And so you've got this really high temperature region right here. And then halfway through the piping, what we have is an expansion valve. And that divides the plumbing into two different sections. There's this first section that the compressor is maintaining at high temperature, high pressure. But then there's this tiny opening, and we looked at some of this too. We saw that if something just expands rapidly, its temperature just drops. And so what's happening is, you can kind of think of it this way, here's this region where it's being compressed, and the temperature is getting really, really high, and then as it passes through this valve, it expands a lot, and just drops in temperature. So all that energy is now gone from the coolant material. And so what we've got now is we've got a coolant, a cold temperature region in the piping. So that's it. You build a compressor, you build a bunch of pipes, you run half the pipes up to where there's an expansion valve, and then the other half of the pipes. And if you keep operating that compressor, this set of tubing of pipes is going to be at a high temperature. The other is going to end up at a very low temperature. What could I do with that? Well, I could put the cold temperature pipes inside the refrigerator, run it in and around all the food areas. That's going to keep the inside of the refrigerator cold. What it will do is it will draw heat out. This coolant inside these pipes is at a lower temperature than the refrigerator. And so heat actually gets drawn out of the refrigerator into the coolant. Now when the compressor pumps the coolant over here, that coolant now that region is at a higher temperature than the environment, and then the heat is drawn away. So it's too good to be true. Refrigerators are the best. Amazing technology. Now for refrigerators, we want to go in and define efficiencies a little differently. In fact, we don't really define it as an efficiency. What we define it as is a coefficient of performance, and that's defined for a refrigerator. That's defined as QL over W. And you can think of it this way. What is it I'm trying to do? I'm trying to move out the QL. And what is it that I'm investing into this? I'm investing the work to run that compressor. So if I substitute this in, as we did before, this COP can also be written in terms of just Q's. And if we use the same reasoning we did before, we can define what's called an ideal COP. An ideal coefficient of performance would be one in which the ratios of the Qs match the ratios of the operating temperatures. So that gives us a COP and a COP ideal for our refrigerator or for our heat pump. So, so here's a comparison here. Heat engine, refrigerator. Here is the diagram we used for the heat engine. You know, the heat's coming through, work's coming out. All the arrows are reversed here. Here we define an efficiency, work over QH, and then we can write it as in terms of Qs entirely. And here we did the same thing for the refrigerator. Now, in the ideal condition is when the ratios of this is from entropy, right? So if we look at the entropy changes taking place as the heat transfers, we find that entropy says the best we can do is to have the ratios of the Qs match the ratios of the operating temperatures. So that condition is on both sides. And then for the heat engine, what that left us with was the ideal, the efficiency that's ideal is to take all these Qs and replace them with Ts, and with the formula can be rewritten this way. Okay. So now the refrigerator, that COP ideal we just looked at is in terms of operating temperatures. There's something called a heat pump, and I'm not sure if we have an example. I'm going to go back to here. A heat pump is actually something that we use. In fact, I just had a heat pump put in this past year to my house. We had a gas furnace. We had a gas furnace for, it was like 20 years old, and we wanted to stop using the natural gas, stop producing carbon dioxide, and so we're trying to get everything in our house switched over so that it's all electrical run. And then what we did, if you watched earlier lectures, I mentioned this, is that we also put in solar panels. So we used that radiant energy from the sun. So we got a bunch of solar panels up on top of the house now. We got those angled to try and get a reasonable efficiency throughout the entire year. And you know, one by one, we've been getting rid of our natural gas appliances, which are all about 20 years old. And so they're all at the, kind of the end of their life cycle, and replacing them with electrical ones. And now we're generating, the panels we have generate enough electricity to operate all of our electrical appliances for the whole year. Okay, so that's good. And the way PG&E works with this is they give you credit on the electricity that you generate with your solar panels. So, and then they average that over the whole year. So as long as during the year we generate enough energy to meet all of the energy requirements for the year of electricity, it doesn't matter if we produce, well, we produce more in the daytime than night. We don't generate much electricity at night with our solar panels. But we generate, you know, it's always during the day, and then our efficiencies are higher in the summer than they are in the winter. But PG&E averages that. Once a year, they tell you how much you owe for the year, and we're right now, the year officially started last April, and PG&E owes us $600 of electricity right now. So we're generating enough that if we switch all of our appliances over, we can go, you know, 100% electrical for our house. Our automobiles, to get electric cars and plug those in, it's going to take a little more doing, but as far as commuting around, I think we do have enough on the solar panels that we have that we could do that. So it would be a chance to go 100% electrical, produce no carbon dioxide with any of the appliances in the house. Anyway, so getting back to the heat pump, and so the way the heat pump works, we now have a heat pump, an electrical heat pump that heats our house and cools it in the summer. And so a heat pump is set up just the same way this refrigerator is. There's a big compressor, and there's two sets of pipes, and there's a reverse valve in our heat pump. So there's a set of pipes that run through the interior of the house into the furnace, And that's what heats up the air, and the air blows past it, and the air gets blown through the house. So in the wintertime, these are in the house heating it, and these are outside cooling the outside, which is kind of crazy, right? So you run this outside, and you actually pick up heat coming in from the outside. Now, in the summertime, if it does get too hot, which it occasionally does, this past year it did. We had some days where it was really quite warm, and it was smoky, and unfortunately, and so there was no way to open up windows and doors. So what happens is you can reverse the expansion valve, or you can reverse the compressor, I guess is a better way to say it. So to turn it into an air conditioner, you reverse the compressor, and now these pipes that are outside are at the high temperature, and the ones inside are at the low temperature. So the heat pump is able to pump heat into the house, or it can pump heat out of the house, depending on what time of the year. And so everything is electrically run, and no natural gas appliances. So anyway, those are heat pumps. Now the heat pump has a little different COP formula, and that's because for a heat pump, this QL gets replaced with QH. And I didn't get that included here, I should have that. But this should be QH over W. If it's a heat pump, then this would become QH, and this is TH. Because for a heat pump, you're trying to bring heat into the house, and that means that the TH is what you want. So it's defined just a little differently, but almost the same. All right, here we go. Let's make some ice. So here is our freezer or refrigerator. It's a 200-watt freezer. It has a COP of 3.8. Now the heat pump that I just talked about with my house, the current kind of new sets of heat pumps that came out this past year, which we got one of the new cutting-edge heat pumps, had a COP of about 4. So which is pretty good. So this is a COP of 3.80, and what that says is, this is kind of remarkable, for an input of 200 watts, I can actually move 760 watts of heat. So you can actually move more heat than the energy it took to move it, and that's why it's called a heat pump. And so the QL here, the heat that's being drawn out of the freezer is 3.8 times larger than the amount of electricity you're using to make your ice. Now here is making the ice. What we're going to do is start with water at 0 and turn it into ice, and I think that's how the problem was set up. So they didn't ask a lot more. They just said, let's turn water into ice. Now the amount of heat that needs to be taken out is 199,000, it's about 200,000 joules. So I need to remove about 200,000 joules in order to make this ice. Now the freezer that I've got this in is able to remove 760 joules each second, and so it says to freeze the water and make ice cubes, it should take 260 seconds or about 4 minutes. And I know what you're thinking. You're thinking, wait a minute. When's the last time you took an ice tray, put it in the freezer, and the water was frozen in 4 minutes? That doesn't happen. It doesn't happen in 4 minutes. Well, what this is assuming is perfect thermal conduction. And so the inefficiencies here are because, if the ice tray is plastic or something. Now, if you go back to the older refrigerators, the old refrigerators that you used to have to defrost, you have to turn them off once a month and let the water unfreeze inside. And they had just the metal compartments. You could drop water on that and it would freeze right away. And so if we had perfect thermal conduction taking place, it would only take these ice cubes a few minutes to freeze. The freezer has enough power, it has enough capacity to be able to freeze that water pretty quickly. All right, here is the heat pump. Okay, so I made the big deal about the heat pump, and here it is. Here is the heat pump. What it's doing is it's using work, and it's taking heat from outside and pumping it inside, but we got to see the actual plumbing. We saw those pipes that the coolant's running through, and forward. All right, so here is a heat pump problem. I apologize. Here's a heat pump problem right here. It's got a coefficient of performance of 3, and it's rated to do work at 1500 watts. How much heat can it add to a room per second? So these numbers here actually look pretty similar to the heat pump that we put in. If the heat pump... Okay. Yeah, let's see what the heat pump numbers look like here. All right, here is that heat pump. Now remember, for the heat pump, the COP is going to be QH, because it's the QH that we want to get. So if it's operating at ideal efficiencies, it says that the input, the compressor, requires 1500 watts, and that there's a COP of 3. So the heat we're going to get is 4500 watts. So, and this is why heat pumps, this is another nice feature about heat pumps, is that if we had an electrical heater, a space heater, with just a heating element, that would say that a 1500 watt space heater can produce 1500 watts of heat. But by actually pumping the heat, instead of just generating it with a heating element, this heat pump is actually getting 4 times as much heat. And as I mentioned, the heat pump that we put in, it has a COP of about 4. So you're only using 1/4 of the energy. In some sense, this thing is like 300% efficient, right? Because it's producing, it's pumping, it's transferring 4,500 watts of heat, but it only required 1,500 watts of electricity to do that. And just for those of you who are thinking in terms of impact on the planet and trying to control the CO2 emissions, heat pumps are also available now as water heaters. So you can get a water heater that's a heat pump, only uses about 1/4 of the electricity or the natural gas energy of a typical water heater. Clothes dryers, there are new clothes dryers now too. So again, based on heat pump technology. So these heat pumps are becoming really big. We're in the process of probably over the next some amount of time getting a heat pump dryer, clothes dryer, and a heat pump water heater. So the amount of energy that would be required for those is about 1/3 to 1/4 of the energy for a traditional water heater or clothes dryer. All right, so if this is the work, this is the QH, this is the QL. Then I guess let me check the questions here. How much heat can it add? Yeah, we already solved that. Okay. So it can transfer 4,500 watts. Now in the summer, when we flip this around, when you change that expansion valve, then it's becoming an air conditioner and it's going to cool inside. And so instead of looking for the QH, now we're looking for the QL. So the COP of QL over W, that's going to drop to 2 for this particular example. And that says that we'll only be able to pump 3,000 watts out of the house. So when we're heating the house, we get the 4,500 watts coming in of high temperature. But when we're pumping air out, then the inside of the house is the low temperature region. And for that, we're only going to be able to pump out 3,000 joules per second. Okay, is the way the numbers work. But heat pumps, they're the best. They're everywhere. All right, so those are some of the devices that we can use, or we can develop with with some of these processes that we've looked at, some using the PV diagrams, analyzing different processes, thermodynamic processes of expansion and compression of materials. So now what we want to do is move on and take a look at, come back and take another look at entropy and try to get a better understanding of just what these entropy processes are telling us. So entropy changes can be calculated in these thermodynamic processes as Q divided by the temperature at which that heat is being transferred. Now, if the temperature is changing during that process, then we have to step back and carry out an integration. So we have to go back and do this kind of one step at a time. So we looked at an example like this at the beginning of the chapter, but now I would like to come back and take another look now that we've had some experience with the entropy. So again, what we're coming back to is this sample where we have where we have two samples of water, one at 20 Celsius, one at 50 Celsius, and what we're wondering is what happens when we put them in thermal contact. Now, since the two samples are the same size, we're going to end up with something with a temperature halfway between, and that's a statistical process. So what's happening there is just through random collisions of the molecules, the distributions, the kinetic energy distributions of the molecules are randomizing to where the molecules here on average have the same energy as the molecules here. So energy-wise, if the first law was of energy conservation was the only law that, the only thing going on here, we would say, well, wait a minute, we could take heat from here, transfer it to here. This could drop maybe down to 5 degrees Celsius. This could pick up that heat and it would raise to 65 Celsius. Now, statistically, that's really unlikely, and actually statistically that's like never going to happen. But again, the second law says that the systems tend towards the statistically most likely distribution of molecular energies. Now, I've put in the word random, but random's not quite correct here. It's headed towards a statistically most likely outcome. So again, if you thought in terms of flipping a bunch of coins, statistically, what you would expect is if I flipped, 100 coins, somewhere around 50 heads and 50 tails would occur. Now, it's not so likely that that one outcome would dominate. I might get 49 and 51, and so there's a range of values that statistically are pretty likely, but then that probability drops off. What are the chances if I flip 100 coins, they all come up heads? And you go, well, that's not going to happen. And so that's kind of what's going on here, is that this would suggest that these samples have organized themselves into those that have more kinetic energy on average and those that have less kinetic energy on average. Whereas this, statistically, this outcome, there's many, many different ways that this sort of averaging could occur. There's many fewer ways this could occur. Now, another thing to keep track of with entropy, as we're looking at these thermodynamic cycles, is that any reversible cycle can be written as a series of Carnot cycles. So the efficiencies, we can have very high efficiency engines that are not necessarily Carnot cycles. See how this sort of heat engine, so here's a heat engine right here, they're replacing it with a series of Carnot cycles, adiabats and isotherms. So we can make any thermodynamic process reversible, and we can optimize the efficiency. But to do that, what we have to do is have the material have be in basically an equilibrium condition at every step of the way. So that would really mean slowing the process down. When we have a heat engine, we don't go through a series of stages of thermal equilibrium. If we ignite a bunch of fuel-air mixture, it's not going to have a uniform temperature throughout that sample. So real-life situations are more complicated, and it's harder to achieve some of these ideals that come from these reversible cycles. Okay, this is just a reminder that entropy is a state function, and that says that if I have a sample and it's at a particular pressure, you know, a sample of gas, and it's at a particular pressure, at a particular volume, at a particular temperature, it has a certain amount of entropy. It doesn't matter the path that it took in reaching that point. So entropy is a state function. It has to do what the specific numbers are. Okay, so here's an example that we can look at. Here is some more water mixing, and I know we've looked at a number of these examples. So this is another one that came up with the slides here. I've got some water at 20 Celsius, some at 24 Celsius. They tell us each one's 50 kilograms. So it's a really pretty good sized sample here. 50 liters or 50 kilograms of water that we've got. And these are the formulas that we had derived before. MC logarithm T over starting temperature. And so I put all the numbers in. Now the things to be careful about here, watch units. This is actually in kilograms. This is in grams. So I actually put 50,000 in here. So since those are kilograms, in my calculator I put in 50,000 grams to make sure I'm in the right units. This is in terms of grams, 4.186. And then the temperatures have got to be in kelvins. So temperatures have got to be in kelvins on this. And here also, for sample B, same thing. I put all the numbers in and I put the temperatures in. Now, what's going to happen here, since they're the same sample size, we're going to reach an equilibrium at T equals 22 Celsius. Putting the numbers in, you can see that there's not much of a temperature difference here. And as a result, the overall net entropy change is really small. These materials did not change their temperature very much. And so the temperature increase on the 20 degree side almost matched the temperature, or the entropy decrease. Entropy increases and decreases, just about balanced out, but not quite. Okay, so even for these temperatures that are really close, there's going to be a net entropy increase, and that says that it's not a reversible process. Okay, it will not on its own go back to two samples at 20 and 24 Celsius. Okay, and that's what this is telling us here. So a few more examples here. So entropy changes in a free expansion. So what we want to look at is a bit of a different type of process here that's called a free expansion. So it's adiabatic. We'll take a look at the diagram and see what this means. But we're going to take some number of moles of an ideal gas, and we're going to, first of all, have the gas at a volume V1, and then we're going to allow the gas to switch over to a volume V2 without having to push anything out of the way. So that's what makes it a free expansion. Now what they want us to do is calculate the change in entropy of the gas, the surrounding environment, and then evaluate the change in entropy for a 1 mole sample. So let's do that. So here is the diagram. So here is my sample of gas molecules, and what I've done is I've got a container here. I've put a barrier so that all the gas molecules have to stay on one side of a container. And then in order to have a free expansion, what we want to do is have nothing over here. So I've got this wall set up, and then we pull the wall out very rapidly. And so instantaneously the gas molecules, instead of being confined to this volume, now have more volume, maybe twice the volume, to be able to move around in. How is that going to affect the temperature of the gas molecules? How much work was done? How much heat was transferred during that process? Now, it's an ideal gas, and since these molecules, the wall was removed here, nothing pushed on the molecules. It's just instead of having a wall at that location, now whenever the molecules come where they would have hit this side, they continue to just bounce to the other side. So the speeds of the molecules were unaffected. The internal energy of the molecules were unaffected. And that says that the internal energy, delta E, going from this picture to this picture, it's 0. We didn't add any internal energy. We didn't take any away. Now, what about heat? Well, if this is an insulated container, there's no heat in this process, and simply because I removed the wall doesn't mean that any heat was added. And so the Q is equal to 0. And then finally, this one. What about work? Because what we've been saying, what we said all through chapter 19 and 20, is that anytime we compress, then energy is being transferred into the sample through work, and anytime we allow an expansion, the energy is lost from the sample. And this at first looks kind of like an expansion, except these gas molecules, when we remove the barrier, they're not pushing against anything. That other side of the container is vacuum. It's been evacuated. And so if the gas molecules don't push against a piston, for example, if this were a piston, then as the piston moves outwards and the gas molecules hit a moving piston, they'll transfer some of the energy into the piston. But that's not what's happening here. So the gas molecules aren't pushing against anything as they expand. And as a result, there's no work for this sample. So there's no exchange of energy with the environment at all. The gas molecules have the same amount of energy that they had before. None of that stuff is changing. And so that says they'll be at the very same temperature. Now, when you ask the question about entropy, I'm inclined to say, well, I didn't transfer any heat. That would suggest there's no entropy increase, but I can see that the molecules are more spread out than they used to be. That would suggest maybe there is an entropy to consider. So I'm kind of in a quandary here as to whether or not there's an entropy change. It certainly looks like things are less organized. Things are more, there's more possibilities out there as to locating these particles. Now, the way we're going to answer this question is to say, hey, entropy is a state function. So on my PV diagram, this free expansion that we've got, point A, I can put that in there, and point B, I can put that in there too. Since the temperature didn't change, I know that point A and point B correspond to the same isotherm. Right? Now, there was not an isothermic process that took place. When I removed this, the molecules immediately started filling this region. And pretty soon, a new equilibrium was set up. So initially, at least, there were pressure gradients that took place here as the molecules found their way over to the other side. But once things settled down, we're back at another equilibrium position. So this has a well-defined temperature, this has a well-defined temperature, these two pictures, but there's no well-defined path in between. Since entropy is a state function, what I can do is I can imagine a path connecting these, calculate the entropy change for that, and then say it doesn't matter how I got from point A to point B. As far as entropy is concerned, any path will give me the same result. If I, first of all, lowered the pressure and then increased the volume, or if I follow an isotherm, whichever path from A to B, whether it's a free expansion, I can calculate the entropy change for the gas molecules using this. Now this is a little different because the formula has changed here. This process is not a Q over T, but we can imagine it, we can replace it with what would have been a Q over T process in order to calculate the value. So here we go. Back when we looked at isotherms, what we're going to do is use an isothermic process to calculate or determine what the entropy would be, entropy difference would be between point A and point B. There is no path. There's no well-defined path that connects those 2 points. What I can do then is say Q is equal to nRT, ln of V over V. That came from earlier when we were calculating work for an isothermal process, and then said that the Q matches the value for work. So this is how much heat would have transferred if it had been isothermal, and then I can divide through by T. So let's do that. If I take the delta S, imagining that it followed an isothermal process, what I end up with is nR, natural logarithm of final volume over initial volume. So that's the formula we get, and that'll tell us for a free expansion process, if the volume starts out at VA and goes to VB, and the sample size is n number of moles, that's how much the entropy went up. If we use their numbers of 1 mole, and then here's the value of R, and then the logarithm of 2, that's going to give us 5.76 joules per Kelvin. Now, they also ask about the environment. So the entropy did go up. I guess that's the first thing we should point out here. The entropy really did go up. It didn't go up because there was a heat transfer. It went up because the molecules were allowed to occupy a broader region of space. Okay. All right, now what about the environment? What happened out in the environment in terms of entropy? And there wasn't any entropy change in the environment between this picture and this picture. We did empty out this part of the container, but that's a separate question. And so the environment, at least during this process from A to B, nothing happened out in the environment. So the environment didn't have any increase in entropy. The gas molecules did. Again, since the entropy, the net entropy increased, this reaction is not reversible on its own. The process will not go back. What I mean by that is this. I'm not going to get all these molecules to go back on this side of the container. Now you're thinking, yeah, but remember, this is all statistics driven. So isn't there a chance, at least statistically, that at some point, all of these molecules would find themselves back on this side of the container, and then I could close, I just wait until all the molecules are on one side, and then I put the barrier back in. And you're going, yeah, it could happen. What are the chances of any individual molecule being on the left side of this container? And it looks like it's 50-50, right? It looks like it's a 1/2 chance. Now, if I extend that to n molecules, that would be 1/2 to the n power where n is the number of molecules. If all there is one or two, or if there's only a handful of molecules inside, certainly that could be done. Up to 1, 2, 3, 4, 5, 6, 7. I might have to wait a while, but at some point all 7 of these would be on one side, and I put the barrier in. But what if I have 10 to the 24th molecules? Just an enormous number. It's the statistics, the likelihood of ever having all those show up on one side is, you have to wait many, many lifetimes of the universe likely to see that event ever take place. Here's another example of calculating some entropies. This one is saying, look, I have a red hot 2 kilogram piece of iron at a temperature of, this is 880 Kelvin. What's the melting point on iron? Isn't it melted by the time you get to 880 Kelvin? I gotta look that one up. That seems really, really high. Anyway, apparently we have a piece of iron at 880 Kelvin, and it's a 2 kilogram piece, and it's thrown into a huge lake. Look at this huge lake. I got this really high temperature piece of iron. We throw it in there. The lake is at a temperature of 280 kelvins. Now, the lake is so large that if I throw this piece of iron in, it's really not going to have any significant effect on the lake. What's going to happen is, well, what's probably going to happen is some of the water is going to vaporize or something, at least initially. They're ignoring all that. So we're imagining there's a way to throw the iron in where the lake temperature, the heat spreads uniformly and the lake temperature is hardly affected. We can treat the temperature of the lake as staying constant. So calculate the change in entropy for the iron and calculate the entropy for the lake, for the environment. All right, here's the plan. Now with the iron, we're just going to go back to this delta S for the iron is given by MC natural log of T2 over T1. We can plug the numbers in. We had 2 kilograms of iron. If I look up the specific heat for iron, it's 450 joules per kilogram per Kelvin. And then I put the temperatures in. Now the temperatures this time are already in kelvins. So I didn't have to change them, but more likely than not, temperatures are going to be given in Celsius. You're going to need to change the temperatures. So the entropy of the iron dropped, and it dropped by 1,030 joules per Kelvin. Now, as far as the water in the lake, what we can do is say there's a certain amount of Q that came into the lake, and the temperature is very, very, very slightly affected, so we're going to treat this as constant. Now, the amount of heat coming out of that block of iron, that was a 2 kilogram piece of iron, and its specific heat was 450 joules per kilogram per Kelvin, and the temperature of the iron dropped 600 kelvins. So this is the amount of heat that came out of my block of iron when it went into the lake. So 540,000 joules of heat went into the lake. Now, we can't tell by putting a thermometer in the lake because the temperature change was so slight, but we do know from the iron that must have been the amount of heat. So I'm going to have that much heat go into the lake, and it's going into a lake, and the lake is at 280 kelvins the whole time. So look, the lake's entropy increase is 1,930 joules per Kelvin. So again, what we're seeing is the entropy increase in the location where the heat's coming in is always larger than the entropy decrease in the object that's cooling down. Okay, so there's a net, it looks like 900, huh? So it looks like there's a net entropy increase of 900 joules per Kelvin for this particular example. Questions on that? Any questions? All right. A couple more things we want to say about this second law. If we look at an isolated system, the entropy is always either staying constant and the processes we're running are reversible, or it's increasing and the processes are irreversible, at least spontaneously on their own. If it's a closed system, then this is going to always hold. All right. What does that say about the universe? So, if what we've been talking about with entropy applies here to the universe at large, what would happen is over time, all of these high temperature regions would cool down, all the low temperature regions are going to heat up, and pretty soon everything in the universe is going to be at the same temperature. Now, what's preventing that from happening right now? What's preventing the entire universe from reaching thermal equilibrium? And currently there are gravitational forces and there's nuclear fusion going on inside stars. So what the gravitational forces are doing is the force of gravity tends to draw objects together. So up until now, when we've been looking at samples, we tended to think of the natural tendency was for the samples to just kind of spread out and fill all the available space, and that was maximizing entropy. Well, gravity changes things around. So when we look at an astrophysical level, higher entropy actually occurs as more things collapse together gravitationally. So it's kind of interesting that that's the case. The universe is still heading towards greater and greater entropy as more and more of the mass gets concentrated into fewer and fewer objects. As material collapses to form a planet, or material collapses to form a star, or lots of material collapse to form a black hole, the entropy is going up with those processes. Those are higher entropy. So if we think of the universe, the lifetime of the universe, what's going on here, this is really weird, but what's happening is the universe in earlier stages was very, very uniform, and that was actually a very low entropy state. Now that things have collapsed and galaxies and stars and have formed, that's a higher entropy state. So kind of have to think backwards at cosmological scales. But it is kind of interesting to think about, if everything were at the same temperature, then, and all the chemical reactions that could run had run, all the nuclear reactions that had run, then we kind of run out of new sources of activity. And all of the gravitational collapse into a bunch of stars and black holes and such had taken place. Then there's no additional chemical reactions to run. You kind of run out of all of these processes. So these processes kind of, processes we're familiar with kind of shut down. During talking about entropy, at several points, we kind of talked about heads and tails and flipping a bunch of coins. And here's a table where they've actually gone through, they've imagined 100 coins, and they've imagined flipping all 100 coins together and then asking what the possible outcome would be. Now, this could be used as an analogy back here, where we were imagining gas molecules. What if we had 100 gas molecules? That's a very modest number of gas molecules. And let's say when I flip a coin, if it comes up head, that gas molecule is on this side, and if it's tails, it's over on this side. What are the chances of having all the gas molecules end up on the same side? And the probability of that is 7.910 to the minus 31. That is a tiny number. That is, that is 1/2 to the 100 power. So that's a very unlikely state for the molecules to be in. Compare that with what's the likelihood if I flip these coins, 50 come up heads and 50 come up tails, and that probability is 8%. 8% of the time, if you flip 100 coins, 50 will come up heads and 50 will come up tails. You go, well, what about 49 heads and 51 tails? That's at 5%. And then at, oh, I'm sorry, this is at 55. Yeah, it seemed like too sudden of a drop-off. So 50, 55, by the time we get down to 60, so 60 heads and 40 tails, that happens about 1% of the time. And so what's happening here is almost all of the probability of these outcomes is bunched in a narrow set of outcomes. If we think of that as molecules in a room, there are not going to be very large fluctuations. The fluctuations are going to get really small once you have really large numbers of molecules. But again, it's statistically driven. Now here, if you think back to chapter 18, we looked at all those molecular distributions, and we talked about how the molecular distributions get set up. There's a certain number of available quantum states, and not every molecule is going to have the same speed. That's what this is showing, but that's very unlikely. We can actually show that what we call, again, the word random probably isn't the best to say. It's probably best to say the statistically most likely distribution, the most probable one, probable state that we will see, and the greatest disorder, I'm not sure about that. That's the one that has the greatest entropy. So the most probable state has the greatest entropy, the one that's going to occur most frequently. If we go back to our coin tossing analogy, it's going to be something within a narrow range, very close to 50 heads and 50 tails. That's going to make up most of the probability that we're looking at. Now, Ludwig Boltzmann, who did a lot of thermodynamics theoretical work, did a lot of work trying to establish the existence of atoms. He was a big atoms advocate. Seems funny, but you know, in the early 1800s, atomic theory was just being established, and it just looked overwhelmingly, the evidence was for the existence of atoms. Everything was made out of atoms, and there was a list of the different elements. And yet 100 years later, a lot of people were starting to think atoms weren't necessarily real. It was just a useful model for thinking about materials. Well, Ludwig Boltzmann said, yes, there are atoms, and he set out to use thermodynamics to explain how heat and work could all be related in terms of the atoms that make up different samples. And he even came up with this formula that the entropy of a collection of molecules is equal to, now the little k here is Boltzmann's constant. So this is Ludwig Boltzmann's constant times the natural logarithm of omega or w. This looks like it's w that they're using here. And this is what's called the number of microstates. So the entropy of a sample, if we go back to this example right here, the number of microstates, the number of different ways that you could get 50 heads and 50 tails. So if you line up all the coins, you line up these 100 coins, and you ask, how can I get 50 heads and 50 tails? Well, the first 50 could come up heads, and the next 50 could come up tails. You go, okay, that's one way it could happen. But then, you know, it could go heads, tails, heads, tails, heads, tails. There's just so many different ways that you could end up with 50 heads and 50 tails. So it turns out that if you look at all the possible ways, it's 1 times 10 to the 29. Now what Ludwig Boltzmann is saying with his formula here is that the entropy of that particular state of 50 heads and 50 tails we can take that number, that 10 to the 29th, plug it into here, multiply by Boltzmann's constant. You can actually get a numerical value saying how much entropy that corresponds to. Now if I look, again, if I use this Boltzmann formula, and we apply it here to this state where everything comes up heads. If everything comes up heads, how much entropy is there? And that's no entropy. So there's only one way that that could happen. So it says that in nature, the distributions that we see are the distributions that are really, really likely. We tend not to see those really unlikely distributions. Okay, here is that free expansion that we just looked at, but now we're going to do this in terms of Boltzmann's formula. And this formula from Boltzmann, S equals K, I think this is in your textbook, shows this on at his gravesite in Vienna, Austria. So we'll have to do a class trip or something to go visit this. But it has this formula written out. So this was what he thought of as his most profound, I guess, discovery of all of the work that he did, and he did a lot of stuff. All right, statistical interpretation. We're back to this free expansion, but this time let's do it all in terms of statistics, and let's see how that might work. So here we are, statistics of entropy. It's a free example expansion again. See how it looks the same as before, but this time what we're going to do is we are going to count the number of possible molecular configurations. And so what happens to these gas molecules is that there are actually different quantum states available. Now we'll see more of this in Physics 4C, but these gas molecules are actually in what we call quantum states. And if we have one side of the container that the molecules are confined to, there's a series of different energy quantum states, different energy levels and numbers of quantum states. If we now allow twice as much volume, the number of quantum, the energy levels, if we go up to different energy levels available to the molecules, there's twice as many quantum states available as they used to be. That's kind of a simplification to use. So the number of quantum states available to these molecules is proportional to the volume. So there's more quantum states when the volume goes up. Now, if we think of molecular configurations, let's say we have 100 different quantum states available to these molecules, and each molecule can go into any one of those quantum states. Well, that says that the number of different configurations would be 100 to the n power. Right? There's 100 different ways the first molecule could select its quantum state. There's 100 different ways the second molecule could select its quantum state. And that would give us 100 times 100. That would give us 10,000 possible configurations. So if I take the number of available quantum states and take that to the n power, where n is the number of molecules, that tells us how many microstates, how many different configurations are there to the molecules that produce a particular outcome. So if we pick up on Boltzmann's formula here, then we can say that when we had a volume that was somewhat reduced, the entropy of this was K times the ln of Ga to the nth. But now that the volume has increased, the entropy has increased, and now it's given by K logarithm G sub B to the n power. Well, the increase in entropy is entropy B minus entropy A. Now notice we're talking about absolute amounts of entropy. It's not just delta entropy anymore, but we're actually talking about a certain amount of entropy for a particular setup. So this becomes the logarithm of WB minus logarithm of W1. Now if I take the ratio, if I take WA minus WB minus WA, That's WB divided by WA, and that's going to be given by GB over GA to the n power. Since this is a logarithm, I can bring the n out front, and it says that the increase in entropy for this free expansion process by counting the molecules and their quantum states is given by NK ln of VB over VA, which the number of molecules and Boltzmann's constant can be replaced by n times R. And look, using purely just statistics, we get the same formula for the increasing entropy for a free expansion. So we can do this in terms of pressure and volume of the molecules, pressures and volumes and temperatures of a collection of molecules, or we can go in and just count the molecules and count their quantum states and come up with the very same expression. I put the numbers in and we get the 5.76 joules per Kelvin that we saw before. Okay, so this is kind of a more fundamental. It's taking it right down to the quantum states and the individual molecules and seeing how entropy can be expressed. Okay, a couple of entropy-related concerns here. Over 90% of the energy in the United States is generated, it's utilized in heat engines. Okay, so we generate a lot of electricity. That's, most of the majority of the electricity around the globe is coming from fossil fuels. Even nuclear fusion is also generating, there are also heat engines. And all of this is, the fossil fuels are releasing CO2, and all of these processes are releasing more heat into the environment. So the CO2 leads to a greenhouse effect, and then the other heating from all of these just leads to warmer conditions, especially in and around cities. You can do these thermographs from space now, and you can see the temperatures in and around the cities is higher because of all the heat that we generate. All right, here is the summary for chapter 20. And we did it all. So we're through all of thermodynamics, and I think we're looking towards getting ready for maybe a midterm coming up here in the near future. We've got a review, we have a review lecture coming up. We'll look at a number of practice sample problems and go through those. But interesting stuff with entropy, and statistically, keeping track of all the molecules and what the distributions of those molecules will be in terms of their kinetic energies and other properties. All right, the end of thermodynamics.